Hello, my name is Juyong Lee. Today, in this session, I'm going to talk about the remote sensing applied for pre-fire management. In this session, I'm going to give you some basic introduction for the sensors available for fire predictions and what are they, how they work, and what information we can get out of it. And in next follow-up sessions, we're going to focus on specific indicators and variables available for the fire predictions and why they are important. And ultimately, in the chapter 4, I'm going to deliver a process, large-scale process that we ultimately would like to look at with this large-scale observations with remote sensing. These are the topics that I would like to deliver, and I will introduce a variety of different satellites and sensors, and would like to address why we need large-scale observations with remote sensing and spatial information as compared to model simulations and local measurement, in situ measurement at the local stations, and why it is needed to better manage pre-fire information as compared to active and post-fire management. And I will briefly talk about technical advantages and disadvantages of currently available sensors, which will include optical infrared sensors and passive microwave sensors and active microwave sensors. Okay, so what is remote sensing? Remote sensing is basically just measure micro electromagnetic radiation that specific target emits or reflects from the distance with no physical contact or disturbance. However, you are going to target a specific reasons in this broad range of electromagnetic spectrum, specifically microwave or infrared or and so on. So, um, so they detect some target that human eyes cannot see. However, it's not like that we can use the entire spectrum. There are the specific reasons which is transparent, because which is called atmospheric window. That's because there's some atmospheric opacity because of atmospheric absorptions by atmospheric gases like oxygen or water vapor or carbon dioxide and so on. So we are just looking for something transparent which never be obscured by anything by atmospheric layers, and so that we can transmit and then read signals from the satellite. So so like I just said, if using this broad range of electromagnetic spectrum, we can read some information that we cannot see from with our bare eyes. So when you detect thermal infrared sensors, wavelengths, we can read the temperature information from the target. This is not possible with our bare eyes. Um, each material reflects and observes different wavelengths in electromagnetic spectrum. So something like there's a spectral signature, which means that there's a unique pattern of electromagnetic radiations that specific object can emit or reflect. So uh, if you define wavelengths and then if you read reflectance, we can pretty much identify the object, what the objects are, as a function of wavelengths. So there's a relationship between the reflectance and the reflective wavelengths of different components, so that you can pretty much infer what the objects are. Um, satellites can be classified into several different types of sensors by orbit, whether it's polar or non-polar, or by energy sources, whether it is passive or active sensors, uh, or the spectra, like we just saw the broad range of electromagnetic spectrum. Depending on which region you are going to use, you can have like visible or UV, IR, and microwave sensors. There are a variety of sensors. Or measuring a measurement technique, whether it is scanning or one-dimensional or two-dimensional or three-dimensional imaging or non-imaging or sounders, resolution type and the quality. There are different type of the resolutions. Radiometric resolution means that's a sensor ability to discriminate differences in radiance. So you can have several different type of sensors by these resolutions. And spatial resolution is the surface area that forms one pixel. So what this single pixel, what the spatial extents this a single pixel will represent. And spectral resolution means a number of or widths of spectral bands that we just saw in the previous slides. So higher spectral resolution, the higher the spectral resolution, the narrower the wavelength ranges for the given channel or the bands. And the temporal resolution means the time, how long it takes for the satellites to complete one orbit. So which also called a visit time. So in case of SMOS, the revisit time is 3 days. It takes 3 days to revisit the same spot. And each sensor has a different type of applications. You can use it for the weather or ocean or the land or even water quality and so on. So there are a variety of different sensors. Then what would be the advantages of remote sensing? Remote sensing and satellites can provide global and spatial information when there's no ground information is available, with no physical disturbance or contact. It provides continuous, regular observations. And in our changing environment, sometimes the assumptions that we made for the model is not appropriate. Something like a temperature, we're going to talk about this a few minutes later. However, sometimes we assume that air temperature is equal to soil temperature or canopy temperature or land surface temperature. However, this kind of assumption is not appropriate. It's invalid in our warming environments. But satellite retrieval algorithm does not always use the same assumption with the model. So if we compare satellite data with the model, then that means that indicates some uncertainty for the same variables, right? Because we use the different approaches and different assumptions. And data usually freely available. However, at the same time, there are disadvantages of remote sensing. It is difficult to have high spectral and spatial temporal radiometry resolutions all at the same time, which means their coverages are very different by the sensor. So if you look at this figure in here, the black pixel means no data. So you have to wait 2 or 3 days to have the data for that pixel or time. So which means that you have to combine, usually you have to combine several different data sets to increase the spatial temporal resolutions. And a large amount of data in a variety of formats can lead to more time and processing. Yes, that's right. Data set have their own data structures and tool require their own tools. So we have to, download different tools and we have to learn about their structures and so on. And there is an issue for the accuracy, yes, because like we just discussed, there is an issue for the atmospheric layers. They sometimes are there's a atmospheric opacity because of absorptions for the gases, and also there are clouds. And there is a vegetation covers, and also it is almost impossible to formulate all the complicated factors from topography and so on, and coastline and so on. So there is, yes, issues. So people often validate their product with in situ measurements from the local stations. However, there's a spatial scale mismatch issues. So, like in case of soil moisture, their in situ measurements actually represent a few centimeters, although, like in case of passive microwave sensors, the setup product represents like 50 kilometers. By 50 kilometers, so their spatial representative is too much different, so they don't actually necessarily need to be the same, but still comparison is, yeah, is recommended, important to validate and compare the yeah, our product. So we need direct measurement observation for that scale. So in case of satellites, we have the spatial scale of a field of view. Field of view is swath width. If you look at in a figure in here, on the right hand side, there's a pixel scale and pixel overlap and swath width. And this swath width is a measure of spatial resolution of remote sensing of imaging system. This is field of view. And the specific angle from a detector or the remote sensors on the axis of remote sensor is instantaneous field of view. So these are the spatial scales that you have to keep in your mind as compared to the model simulation or the in situ measurement at the local stations, because those are quite different. So like we just discussed in the previous slides, these satellite pixels and spatial resolutions is not something that we can easily, conveniently get from the extrapolation of model grid or from local stations. If you look at the figure on the left hand side, this is the relationship. Differently sampled in a different spatial extents. This study group found that their means and standard deviations of point scale measurements were quite different depending on how you sample them. So if you look at the figures and images on the right hand side, usually like local stations are just point based on the very bottom. So for example, if their measurement was like, for example, like 100, let's say just 100, and then your satellite footprint on the very top could be like 10, because they are a mixed picture. They just mix all the information in this square, and which is quite different from those model grid and in situ measurements. So in situ measurement, more like they just represent just point-based spot, although all the adjacent areas are quite, lower or quite higher from their just, a few points values. However, in case of satellite footprints, they just try to look at all the just overall mixed estimations instead of a few points, extreme outliers. So the estimation may represent quite different spatial extent. So bottom line is that although you combine and take a spatial averages of like 100 point samplings, point scale sampling, then does not conveniently necessarily represent a spatial footprint scale. So that is the issues in here. Fire management, because if we can make a very efficient pre-fire information estimations, then we can have more preparations, and we can take more better um, reactions, response to the natural disasters. And Modi's product provides active fires and sometimes like smoke information, like as post-fire management, and they are more or less well describe the burned areas and fire burned areas and so on, and even carbon emissions. However, there's a lack of information for the pre-fire stage, although despite the high demands. Okay. So fuel moisture would be one of the fuel conditions, which is defined as the ratio between the quantity of water, fresh weight versus dry weight, and either fresh weight or the dry weight. I'm sorry, yeah, just quantity of water over the dry weight. Yeah. Currently, fire fuel moisture is modeled by weather information such as humidity, precipitation, and so on. So we have this much precipitation today, and what would be the fuel tomorrow, moisture would be in tomorrow, and so on. And ignition and large-scale spread of wildfires pretty much depends on the fuel moisture and weather conditions. If you look at the figure on the right-hand side, these are the three elements needed for the fire occurrence, which include oxygen, fuel, and heat. So as long as you understand the fuel and heat and oxygen, you can pretty much predict and evaluate the severity of the fire. Yep. So if any of these are lost, then fire will dissipate, right? So our purpose is to get rid of one of these elements. And oxygen is almost impossible, unmanageable. However, the heat and fuel, maybe we can do that with hydrology, with our hydrological and forestry knowledge. However, unfortunately, there's a lack of near real-time observations for these two elements. Fuel, no. Heat, no. So currently, we just indirectly use evapotranspiration rate. However, we are going to talk about some limitations and difficulties in doing this later on in following sessions. So these are the fire development. If you look at in this yellow line, as temperature goes up and fire actually go through preheating and ignition and combustion at max. Yeah, so there are three phases to wildfire: pre-ignition, just before this max of yellow line, and the max would be the combustion, and then after the combustion, we're going to enter extinction. The important thing is that as long as we accurately reliably monitor this temperature, we can pretty much predict combustion ahead of combustion just by looking at the temperature increase, right? Yeah. Current Modi's fire products pretty much focus on this stage in the green box, glowing, like smoldering, and smoke and fire, active fire, and so on. However, we would like to improve the fire prediction in this earlier stage in the blue box. Fuel preheating and ignition and so on. So we would like to look at the preheating, fewer heating, available in the form of energy before that is escalated to the smoke or flame, something in the later stage. So that we can make a prediction ahead of combustions. Like I said, there's a pre-ignition phase. In this phase, there's a preheating. During this preheating phase, vegetation reaches the temperature which for which vegetation forests start to ignite. So you can see that how much important it is to properly, reliably, accurately fewer temperature. As vegetation is heated, we're going to lose the moisture, so fewer moisture will decrease. So as long as we can reliably observe a vegetation heating process, we also can infer fewer moisture. The presence of heat radiating from the flames of wildfire, can propagate and preheat nearby adjacent forest and vegetation fuels. So if there's a fire occurrence, if fire occur, and then they can propagate, they cause preheating of adjacent unburned forests, this will, fewer more other adjacent fuels, and that's why the fire spread can be accelerated. So again, monitor preheating, vegetation heating, and fewer heating is very important to predict a fire spread. That is bottom line. When we say fewer, this includes leaves, woody debris, decaying organic matters, grasses, trunk and branches, and shrubs. The reason that I mentioned about this one is usually when we most of studies deal with vegetation index, just to look at vegetation properties. However, vegetation index pretty much only inform about leaves, live foliages. However, the trunks and branches and shrubs, even woody debris on the floor is still important to detect and observe for the wildfire applications. And the other point is that when there's a storm, storms down the larger amount of trees or pests are spread, these are also another cause for spreading wildfires. So decaying material that dries and burns easily. And so the density of forests obviously plays an important role, because dense boreal forests, actually, increase fewer availabilities and more important to monitor them. So even cut down the trees are really important to maintain soil moisture and to reduce fewer availabilities. Although most of carbon policies pretty much regard forests as a carbon sink, however, in these days, as things are getting drier and getting hotter, and we are entering extreme heat events, the mechanism of forests is getting more diverse and more complicated. Yes, it's true that for the long term, forests has the effect of cooling. They are very effective at carbon sequestration. However, for the short term, forest has the effect of heating, right? So when there's a vegetation heating, this becomes more vulnerable to wildfires and making huge carbon emissions. So forests as the carbon and heat source in extreme hot heat events play a role of the catalyst for more destructive wildfires, and ecosystems are amplifying this feedback, increasing fewer temperatures and increasing sensible heat they were gonna increase vegetation heating, then more bigger fires and more carbon emissions. So just planting more and more trees and increasing forest densities and decreasing fuel moistures and increasing fuel availability is actually we're entering vicious cycle of increasing more carbon emissions. So we need information and observations at a large scale, what's going on in there, whether the forests are capable of carbon sequestrations or they are more vulnerable to wildfires, so it's likely to increase carbon emissions. Yeah, to make a evaluation for that, we closely have to monitor forest temperature and fuel moistures. However, it hasn't been easy to have that information because currently available live fuel moisture content, which are called LFMC, which is based on Moody's leaf area index or NDVI, stuff like that, but um, which actually more specific to vegetation chlorophyll instead of the moisture itself. And if you look at some local authorities' observations, temperature, forest heating, and temperature increase is really, quickly made. Like within several days, the massive amount of snow is just totally melt down, and that makes sufficient amount of heating to trigger the ignitions and the fires. However, this several days of time evolutions cannot be detected by vegetation index because vegetation index, you know they don't change their chlorophyll contents within several days, right? And another application was to use land surface temperature from the model. However, from the satellite, something like thermal infrared sensors like MODIS. However, in thermal infrared sensors, forest emissivity is affected by hydrological factors such as like precipitation, snow cover. However, these are not considered, not included for their retrieval algorithms, and instead surface emissivity for the forest regions are usually linearly approximated as a function of vegetation index. However, like we just discussed, they don't really represent moisture contents, they represent chlorophyll. If using the model to estimate land surface temperature to infer fuel conditions or fuel temperatures, they usually use energy balance equations to retrieve land surface temperature. However, they assume that there is no heat capacity on the surface. So the heat storage factor is not their interest. Or sometimes air temperature is being used for the land or for the fuel temperature. However, there's very low dependency on the vegetation conditions when you use air temperature. Air temperature is 2 meters high from the above vegetation. So although they are often assumed to be equal to the soil temperature or canopy temperature, air temperature total represent, I would say quite different characters from land surface, especially vegetation. That is so much true, especially for heat wave conditions, under which canopy temperature is usually higher than air temperature. Yeah, so there's some very important temperature gradient missing from our current platform. And sometimes, like C-band SAR is often used for estimating the fuel conditions like vegetation moisture. However, we're going to discuss about this later on, but it's very challenging and tricky to isolate moisture elements only from a complicated backscattering signature. So far, we don't really know whether heat waves in the next week or this week will be escalated to the ignition of large-scale destructive wildfires or not, whether we're going to enter the vicious cycle